In this last example, we'll look at how the loading of the transistor affects the properties of the transistor. And we sort of touched on that on the last example, but we'll use Thevenins this time to actually work it out what's going on. And then subsequently Vin will change. If we use one of the previous examples, we said that for the 300 milliamps to be flowing through the lamp, we'd worked out that Vin was 2.2 volts, and for that to happen, IB was 1.5 milliamps. Okay, just reminding you there we have IB going along there. If we focus on the light sensor, we've designed and created a light sensor that when the light level falls, the LDR's resistance is 3 kilo ohms. So we measure that out of circuit, and then we built our light sensor, and we wanted to test our light sensor. And then in testing our light sensor, our voltage, just purely looking at as a potential divider, and we're going to have 3 over 3 plus 6k times by our 10 volts. So our light sensor at that particular light level is going to give us 3.3 volts out. Okay, so we put the two halves of the circuit together, so we know that our transistor part of the circuit, if we've got 2.2 volts as V in, then we will have sufficient current, 300 milliamps, for the lamp to flow, and obviously our light sensor there should be giving us 3.3. However, the unfortunate situation is the bulb doesn't light, so we need to use Thevenins to analyse why the circuit doesn't work. So if we apply Thevenins to the circuit, the first thing we do on Thevenins is to calculate the voltage open circuit. So then when we're looking at our sensor, that's just going to be the voltage there, what we normally have as our normal V in, or would be our normal V in. So we've already calculated this. Then the next step would be our current short circuit, where we're going to be shorting out effectively the LDR in the circuit. So it's going to be voltage divided by resistance, our 10 volts divided by just our 6k gives us 1.67 milliamps. And then finally we're looking then to work out our equivalent resistance. So that's our voltage open circuit divided by our current short circuit. So we're going to have 3.3 volts divided by our 1.67 milliamps gives us approximately 2 kilo ohms. So we'll use 2 kilo ohms in the circuit. So the next job is for us to draw our Thevenins equivalent circuit. So there we have our equivalent circuit. So we've got our equivalent resistance 2k, our voltage open circuit 3.3 volts, and this is where normally our load would go. But this is so our load effectively is our transistor circuit. So V in new, because that's what the problem is in the circuit. We think we're supposed to have 3.3 volts, but actually what we're doing is loading our circuit, so we haven't actually got that. So we need to then carry out a calculation. So in calculating what our load is going to be, so it allows us to calculate what our new V in, we need to take into account the transistor and the safety resistor. Well, luckily for us, we've got the old V in. So resistance is equal to voltage divided by current. So in particular, it's our old V in and our original IB. So we said we got 2 volts. 2.2 volts and 1.5 milliamps gives us 1.47 kilo ohms. So we can now put that into our circuit here. So we've got 1.47 kilo ohms is our resistance, which means then we've now got a nice little potential divider, so we can actually then allow us to calculate what the new V in is going to be. So the new V in, so the voltage of our load, so 1.47 kilo ohms over 2k plus the 1.47 kilo ohms times by our 3.3 volts. If we're just using the quick ratio method, of course you can do it the long-handed if you prefer, but the long and short of it is, if you do that, then all we've actually got then is 1.4 volts. So let's just summarize. So we've built our transistor circuit and everything seemed to be all right. We needed a V in of 2.2 volts to get our current flowing through our lamp. We built our light sensor, and everything else on the light sensor circuit seemed okay for the particular lighting condition that we wanted. We've got 3.3 volts out of it, but then when we connected the two subsystems together, unfortunately we had a interface issue. There was a loading of the circuit, and actually when we connected the two circuits together, instead of having 2.2 volts there as our V in, then as we've just worked out, we had only got 1.4 volts as our V in, which meant that we're no longer just saturated, we're somewhere within the linear region. Okay, so to bring it all together, how do we work this out? Well, we've seen before that when we're connecting subsystems together, that the output resistance should be small compared to a large input resistance, and we've used the idea of 10 times. Well, here's exactly the same style, whereas the current that we have in the potential divider needs to be 10 times that of the current going down in the base. So we had only actually got 1.1 milliamps in our potential divider. Our current down in our base needs to be 1.5 milliamps. So the divider current should have been at least 15 milliamps. So ultimately, the resistance of our input circuit, our light sensor, needs to be a lot smaller so we can get a greater current.